Hello guys, Cyprien from FE for All, and in today's video we'll have a look at how to simulate this kind of heat case, and this will be a thermal analysis. So I got the feedback from you, from the blog, from the comments that I haven't done any video about transient thermal simulation, and I decided to correct that. So I'll start by showing you how to simulate that as a static thermal analysis, because it's still important to know how to do this. There are a few tricks that I'm not necessarily showing in the previous videos that will be useful for you. For example, how to define the material properties for thermal, the contacts between the thermal parts. All these things are very interesting to learn. And once I'll be able to show you this, we'll have a look at how to make that a transient analysis by basically changing the temperature applied to this. So as a good engineer, before starting a simulation, you have to think about the input of your simulation. So what will be the material I will use for that? What will be the loads? And basically what I will do is that this main part here will be in brass, and this one will be in aluminium. So this is the brass material and the different kind of material coefficients that will be useful for this analysis. So for pure thermal analysis, you don't need the Young's modulus or the Poisson's ratio. You just need the conductivity, the specific heat, or in the case of Codaster, you need the heat capacity. So that's why I calculated it. I'll talk about it a bit afterwards. Then same for aluminium. And what I'll do is that I apply a source, so a power source here to this part, and I will apply a convection to the whole rest of the surfaces of this model. Okay, so let's start. I'd like to go totally from scratch, so I'll just create a new project here. Set this one, and I'll just open a blank project. Okay, now let's go to the geom module, in which I will import my CAD file. So I'll provide the CAD file in the comment of the video or on the blog, so you'll have the link there. Okay, the model is imported, and as you can see, there are two parts here, but if you look at the tree, there is only one object here. And so the first thing to do is to kind of separate the solids which are included into this file. So to do this, go into new entity, explode, and you have the option to explode into solids. Okay, so after you've done that, you'll be able to look at each of those two parts separately. Okay, good. Now we need to create the groups based on this geometry. So there will be one group for this part, for the power source, and one group for the convection. So let's create the convection first. So first I hide this body here and keep only this one. Then go into group, create group. Make sure to select the body one here. Select the faces, and you see there is an option select all. So I'll click on that. I'll add everything, and then I'll go and select this face, and you see this is the face with ID number 3, and I just click on remove. That way everything will be selected except this face, because this face is just behind my other part, right? So no convection applied to this one. It's not in contact with air. Okay, let's apply and close, and let's just, okay, we'll rename that to convection BC. Let's just activate this, okay? And you see that this face here is in a different color. That's because what we are seeing here is the external surface, so at the exception of this one. So this should be good, right? We will check later on the mesh groups. Okay, now this is done. Let's create also a group for this, which will be the power source. So group, create group, volume. This time it's a volume group because power is a volumic type of load. And let's call that power BC. Maybe apply. Okay. Now we got the geometry is ready. And I can go into meshing. So let's open the SMesh module. And let's create mesh set for each of the bodies I have here. So first of all, create mesh for the body one. Let's use the free volume NetGen 1D, 2D, 3D algorithm. This one will be easier to mesh all this. And regarding the meshing parameters, so generally let's just use that and see what I get. Compute. So I don't see it because I think it's too small. Yeah, okay, it's here. Okay, so this mesh is really coarse, right? It's you can see this is much coarser than what I want. So let's remesh that. Let's just delete the mesh, clear mesh data. Let's change the hypothesis parameter. And here, so I could, like that, 001. I did some tests, and I found out that 0.003 is, I think, pretty good. So now there's an option for second order element. So in normal condition, I would check this option, of course, for mechanical, because it's much more accurate. Now for thermal analysis, I think code Aster is actually working better with first order mesh. So in case you know about that, please leave a comment. Let me know because I'm not totally sure, but I think it's better to leave it as a first order. So I'll do this and let's remesh. Okay, and that's much better, I think. Could still decrease a bit, but well, let's use that and we'll see. And let's mesh the other body, this one. So I'll do exactly the same thing. I will use the same parameters. So the mesh size should be equivalent. Let's compute that. Okay. Yeah, so now it's correctly here. Now let's create the mesh groups. So let's click on the mesh one. Mesh, create groups from geometry. Now the mesh one is selected. Yep. So let's select convection boundary condition. Apply that. So you see it appears here. Let's select the mesh 2. And if you click on a small arrow here, it changes the mesh. And let's select power BC. And now I have assigned it to the body number 2. Okay, so the mesh group should be okay. So let's hide that. Let's have a look. Always good to verify the mesh groups. So here it's a surface groups. So you see this is void inside. And here is green because we are looking at the other side of the mesh set. So it should be good, right? And here this is my power BC element. Okay, great. Now the dilemma is that if I directly import that into Codaster, I will be getting two mesh sets which are separate, and it will be very difficult to do the simulation out of this. So the trick here is to select those two and use this useful function called build a compound mesh. And once you have this compound mesh, don't forget to create the groups. Create groups from input objects like this. And what this basically does is that it creates one compound, you can see, which has the two mesh sets inside it. And it also have all the groups that have been defined on both mesh sets. You see that I have the power BC here, and I have the convection BC, and I have also some volume groups for both mesh sets. So this is the mesh I will be using for the simulation. Now, if this was possible, what I would have done in another software maybe would be to get the exact same mesh on both faces of the interface here and just merge the node between the parts so that you know, I wouldn't have to define a contact or something like that. And actually, when you use the compound mesh, you do have the option to merge the coincident nodes and elements. But in this case here, because I mesh those separately, there are very few chances that the nodes on the side there will be the same as the node on here. So what I'll do is that I will use specific type of thermal contacts in the solver that will basically do the trick. So I don't care if those nodes are not merged together. Okay, and now don't forget to save. Now the mesh is ready for simulation. So let's go into the Aster study module. Choose the CodeAster stable version. Let's create a new stage. And in this stage, the first step is always to read a mesh. So let's read the mesh, and I will read my compound mesh. Okay, so this is all what I have to do, and you see that I have both mesh set into this model. Okay, so now the read is done. Let's create a finite element model for this. So click on finite element assignment, then choose. So we will assign to everywhere the same model, right? So everywhere this will be thermic, and this will be a 3D type of thermal simulation. Okay. Now comes the creation of the material model. So go into material and choose the define a material command. So in previous video, when we were doing the structural analysis, I mostly chosen this one, linear isotropic elasticity, ELAS. For thermal analysis, there are several models available, and the easiest way to see which model are available is to type like that, THER, and let's look at the keywords only. And you have all those kind of models available for thermal materials. So generally, if you want to know which one is to be used in the simplest case, it's the one that has been translated. So this one, THER, like thermal, is the one which corresponds to isotropic heat conduction. So that's the one I will be selecting. So edit that, and I will have to create two material. So the first one will be brass. So I'm changing the name to brass. And there are two parameters that I need to input, the thermal conductivity. So if you remember from the Excel at the beginning, it was 159. And the volumetric heat capacity, in my case, it's 3.24 power 6. Yeah. So the thing which is slightly tricky is that this volumetric heat capacity is equal to the specific capacity multiplied by the density of the material. So if you have the specific capacity, don't forget to multiply it by the density, and all should be in a meter unit. Okay. So this is okay for the brass. So I created my brass material. Okay, let's go and do exactly the same thing for the aluminum. So I will call that alum isotropic heat conduction. This time it's 200 thermal conductivity, and here it will be 2.43 power 6. Okay. Now those two materials are defined, we need to assign them to the two parts of my model. So let's go to material, assign the material, and select the whole model. And now we have to select each part. So instead of assigning everywhere, let's choose a specific group of elements. And in this case, volumic elements. So I'll choose the volume element from the first mesh sets. This one will have the brass material. And I'll click on the plus here to add the second mesh set volume. This one will have the aluminum. Okay, 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 done. Now we need to assign the loads. So let's go to boundary and loads. And the load to choose here is, so we'll do a static thermal first. So assign thermal load AFE car therm. So this is the one for thermostatic. And I will separate the different loads. So let's assign first the source. So I'll call that source. And you see that there is a source keyword. So I just have to activate this. And here I need to input the source value. So let's go back and look at the Excel, how much it was. So the Excel tells me that in meta unit, it's equal to 2.2 power 8. 2.2 power 8. And I will assign that to the elements of the volume 2. So I could choose the power BC actually that I defined. And it's exactly the same. You see the number of elements is the same, but this is one I created, so I will use this one. Okay. Let's now define the convection code. So I will go in the same place. This will be convec. And here there is no convection keyword. Well, that's because in French it's called échange. So that's the one to create a convection. So if you look at it, you see that it asks for a group of elements. So I need to use the surface elements here that I define. That's where it becomes useful. Then I need the H coefficient. So the H coefficient was 30. Let's have a look again at the Excel to be sure. So here again, be careful about the unit. So it's 30 in watts per meter square, 30. And the ambient temperature is 55 degrees in my case. 55, okay. Okay, and now there's something lacking for this model, and I talked about it in the mesh definition. It's the contact between those two parts, and this is done as a load. So if you were tempted to use a command called defi contact, don't use it. It doesn't work. It works only for structural analysis. So for thermal, you have two ways to assign contact between parts. So let's call that contact. The first one is the one that I will use, is to use this liaison my, which means a link between the mesh. And this is the easiest way because it basically requests you two 3D mesh sets and it will automatically create the contact between those two. So it's very easy to use. The other thing you could do is to use this échange paroi. And this one would basically link the contact face of this, the surface, to the other surface. But then you would have to define an H coefficient for the exchange between those two. And also, I think you need the same, exactly the same nodal positions as well. So it's not really doable in this case. So let's use this one, liaison my. So I need to define the group maître, so master group for this. So it will be this one. So we need to select volume element, and the slave will be this one. Okay, and that's all we need for the contact. Okay. Now let's go for the analysis, and let's choose thermics. So you have linear thermal analysis. So that's the one I'll be using at for this. So loads, and now we need to define. So I have 3 loads here. So load source, load convection, and a third one for the contact. Okay. And this is done. And now, if I wanted to calculate some more fields, I could use calcchamp. Let's have a try. So thermics. So for example, if I want the flux of temperature, let's do that. Let's add the flux at Lga, Lno, and L at the nœud. So just a small reminder, Lga means element ghost point, Lno means element node, and nœud means node. So, and you need to have those 3 if you want to calculate the flux at the node. The name here should be the same than this, so raster, like that, or you could also check this box and this would automatically consider that. Okay. And the last step is to set the output results. So choose a location. So yeah. Choose the format, and here don't forget to add the results. So classic mistake again, you have to add the result from this, otherwise you'll get a blank result file. Okay, and this analysis is set up, so we are ready to solve that. Let's go in the history view here. So it's a very small tab, but it's a very important one. Then we need to add a current case and add a stage, and here you have the run button. Okay, should save my study. Yeah, run. And now we basically have to wait and hope that this will turn out green. And if it does not, we have to look what is the problem in the message file. And I seem to be lucky. Now it's green. So it means everything went well and I can have a look at the results. So let's go into the case view again and data file. And this is the computed results. They are saved into this file. So right click and open in Paravis. And here, this is my model. Let's have a look. So I have all these 4 types of results saved into it, the temperature and the flux. So let's look at the temperature. And yeah, so here, this is, I think, pretty good. I can activate the mesh. and we see the maximum temperature goes to 140 degrees, and the minimum is 91 degrees Celsius. So I think this is pretty good. I like to set up the number of colors in the color map editor to get a view like that. Okay, let's have a look at the flux. And this is it. So I guess maybe the mesh here is not good enough to have an accurate flux of temperature. So maybe this is, I suppose this value is a bit too large. So if you want to have a good flux, you might have to refine the mesh. Okay, and that's all for the static analysis part. So now let's see how to modify this model to go into to do a transient analysis. Okay, so I'm now back to the Aster study module, and let's see how to modify this model so I can take account of time. So the first thing I want to be able to do is the source load that I am applying to this part. I want it to have a value that will change with time. So to do that, I have to do two things. First, create a time function, and then create a new transient load that will replace the power load that I have here. So let's go for the creation of the function first. So go into function and lists and click on define functions. And the first thing to do is to create some coordinates for this function. So there is no value here, but you should understand this is a time function, and I will show you the parameter after. And I want, let's say, instead of applying a value of 2.8 power, so the value was 2.2 power 8, instead to applying that at time 0, I want to apply that, let's say, 10 seconds after, so in a linear way. So I'll put this value here, and this value will be initially 0. So I have a function that from time 0 to 10 seconds, it will increase with time to 2.28. I have no idea if this is too fast or too slow for the moment. This is just the beginning. Let's click on OK. Let's give a name to this function. So I'll call that source f, like a source function. I need to give it a parameter name. So this will depend on time. And if you look at the initial keyword, the keyword is inst, like instant. So that's why it's called inst. But basically, it is a time parameter t. It would have been better if it was called t, but you know, now it's called inst anyway. And let's change to see those names because that's the one some of you are more familiar when you look at the conf file. So the thing I need to define now is the interpolation, because I just gave it 2 points, right? So what will be the interpolation between those points? Well, I have choice between linear, nonlinear, log. This will be linear, so just a linear curve. It's not a curve, but and now I need to define what I will do at the two extremities of this curve. Let's say, what if time goes over 10 seconds? What will happen? What if time goes below 0 seconds? So I have to activate this prol droite and prol gauche, which means basically prolongation at the right and prolongation at the left. Because droite, it means right in French, and gauche means left. And let's put linear for both. So you'll see that I'm making kind of a mistake here, but I'll show you afterwards, and we'll go back to correct that after we have a look at the results. So make sure you follow through all the video to understand. Now, okay, I created this function. Now I have to create an actual transient load, because this load that I created here is a static thermal loading. So if you go into BCN loads, go down, so it's a bit difficult to find out where this is because the names are kind of, I'm on the Windows version right now. Okay, it's here. You see you have affect, char, ther, f, which is a variable thermal load. So that's the one I need to create now. Let's call it power, and this will be transient. So power T, like that, with an underscore. Let's create a source, and I want that applied to my power BC mesh group. Okay, like that. And the source function that I created before is defined here. That's it, and that's the only thing I need to define. Okay, so now I have this function assigned, and I have my transient load defined. Now, what do I need to do? Well, now the kind of the difficult thing to understand here is how do I actually do a transient thermal analysis? And my first, let's say, reaction when I didn't know how to do was, of course, to go into analysis, look at the different types of analysis available here, and I see that for thermics, I have therm linear, I have therm nonlinear, and I have therm nonlinear mo, which I don't know what it is. So basically, you have two types, linear and nonlinear. So you don't have transient. So how does the transient actually go into play? So it's not, you do not have to do a nonlinear analysis here. Nonlinear is for example, if you have a radiation load, which is a nonlinear type of thermal load, you will have to use nonlinear. Or if you have nonlinear materials, things like this. So let's quickly have a look at the documentation of Codeaster, which is on the website. So if you go on the codeaster.org, you go to training, basic training, you will find those kind of training PowerPoints, which can explain some of the stuff. So it's not explained very well, but you will have some indication. So I click here on thermal analysis, and if you have a look at this PowerPoint, you will have some clue about how do you do the transient in comparison to stationary analysis. And the clue is that you see that you have two operators, therm linear and you have therm nonlinear. And when you do not have eta init, initial state, it means it will be stationary. But when you have the eta init defined in your command here, this will be a transient. So the only difference is that you need to define this eta init. And transient analysis will need an initial kind of temperature defined on your model. So let's go back now to a problem. So let's double click on the analysis here, which is linear type. And if we see we have initial condition, so if I look at the keyword, it's the one that I just showed you, eta init, which means initial condition. So I have to activate this, and I have to give it something. So I can either create a temperature field and associate it to it, or I can simply give a constant temperature value on all the models. So that's what I'll do here. I'll say that initial state of my model is the temperature everywhere will be equal to 0. Okay. Now, second thing I need is to add some increments because it needs some increments to solve according to time. So if I click on that, I'll see that I can define some increments here, or I can pass it a list of instant. So that's what I'll do. I'll just define this kind of list. So, and to find this list, I don't know where it's located in the menu, but I know the name of the comment. So you have the ability to click here, show all the comments. And this comment is called defi list. Sorry, it's called def list, defi. I think it's defi list something. Ah, it's here. It's in function and lists. Defi list real, real. So double click on that. Let's give it a name. Let's call it time list. And this list will contain basically the time instance. So let's give it start. So if you see a debut means start of the list, so that will be the first value of my list, 0. And I needed to give some intervals, so some steps. So jusqu'à means until the last value. So when do I want my time, basically my time calculation to end? What will be my last time instant calculated? So for this first study, I'll just put 100. And I want to calculate every 10 steps. So basically, it will calculate once at 0, one at 10, one etc. every 10 increments. And let's click on OK. Now my list is generated. Now I can go back to this and I can again, so this is time stepping increment. I can pass it my list by activating this option here. Now let's not forget the load. So I still have my previous power stationary load assigned. So I will instead assign my power transient, power T load. And that's all what I need for the moment. So let's save that. Let's go to the history view. Let's run this case. And let's pray that it works. So it seems good. I see some instants which are calculated. So you see now the simulation is not done at once. It's done step by step. And it's almost over because I have defined 10 time steps. Okay, it's done. I'm getting green. Very good. Now let's go back to the data file and let's have a look at the calculated results. Okay, so let's have a look at what we have calculated here. So let's look at the temperature. And so everything is blue. That's because I am at the first time step. By the way, it's useful to open the time step window, which is called animation view, where you can see all the time step, and you can like that select one specific time step. Now you can also use this to play or to go to the next frame. And what you see is happening here is that the first step everything is blue and then everything becomes red. So it's pretty weird basically. And the reason for that is that the first time you open the results, the scaling of the legend will be equal to the first to the results at the first time step. And because my first time step, the temperature is 0 everywhere, basically my results here are almost 0 everywhere, and it becomes like this. Now, how do I correct that? Well, the way is to go to the last time step, and then you have an option here called rescale to data range over all time step. And if you click that, yes, I want to do this to all time steps, and you see that you finally get something that looks good. And let's have a look at the animation. You see that the temperature increases and up to a certain point. Now, okay, that's cool. I was able to do a transient analysis. I show you how to, to solve and get some results. But what about the actual results? What about the accuracy of the result I'm getting? Because this is ultimately what is important, right? So let's have a look at the temperature here on the chip. So I know already it's around 400 degrees, but I like to put a probe here to kind of see how, oh, and by the way, I don't really need this animation view, so I'll just hide it again like that. Okay, so I put a probe here, and then you need to have this selection display inspector view that you can also activate, and you can like that show the temperature at this position. So now if I navigate back on different time step, so I can put 2 points, one here. From the first time step is 0 everywhere. You see temperature increase, 40, 80 degrees, 120, 160, 200. So it's basically increasing quite a lot, right? And very rapidly. How do I see the actual evolution of the temperature? Well, the easy way is to go into Edit, Find Data, and the nodes that you have selected, or you can select them now, you can basically click here, Plot Selection over time. And this will directly open a second window with plotted results. So this is the temperature, and if you go in this properties window, I will only display, let's say, temperature results, and it basically gives me the results at between the 2 points that I selected. So that's why I have this big red. So the top result here is 300. So, and this is the point here. So if I have only 1 point, it would give me one curve. But the important thing to see here is that from 0 to 100 seconds, temperature basically increases exponentially. So it doesn't seem like it will stop. And that's not what I hoped to get. Because if you remember, the static analysis result showed me that the stationary temperature at the end would reach 140 degrees around the chip. So, and this is already 2 times higher. So this is obviously because I did a mistake in, so that's what I was mentioning before to you. Let me delete that because it takes a lot of memory space into my project. Let's come back to Aster study. And let's have a look at my source f function. And if you remember, I set the right extension, left extension of the curve as linear. So which means basically that my time here goes between 0 and 10 seconds, but my actual simulation time step go between 0 and 100 seconds. And the linear extrapolation, which will go at the right of this value, will make it that this values of power will rise linearly with the time. And I don't want that. I don't want this to rise linearly according to time, because it means that it will become really, really hot. And I want basically this to be the maximum value, the cap value that it will get to. So the only thing I need to do is to go to the right extension and change to constant. So that way, the function will go like that up to 10 seconds, and then it will remain constant at 2.2 power 8 for this value. So let's save that. Let's recalculate. Let's see if now the results are better. So let's have a look at, again, those calculated results. Temperature. Let's have a look at the maximum. So let's go to the last time step, and let's rescale again to the data range. And we see now that the maximum temperature at the end of the 100 second reaches 64 degrees. So if, again, I plot the curve, find data, let's Let's select this node here, plot all the time. Let's plot only the temperature. Now we see that the temperature here at this point goes over 64 after 100 seconds. But this time distribution is not increasing exponentially anymore. It's basically, increasing, and we see that it starts to kind of converge towards a certain value. And we know from, because we did the static stationary analysis, we know that the final value should be 140 degrees. So we'll start pretty far here. We are at 64. And this basically means one thing. It means that the time 100 seconds is too short to actually get the final stationary result of this analysis. So I have again to go back and recalculate. So again, I'll delete that. So why I'm deleting this is because if you don't, your HDF file will become huge. So I'm just deleting that. Now let's come back and go back to data setting. And basically the way to set up this simulation time is to go back to my time list. And remember that I told it I want to calculate until 100 seconds. So let's change the time to 1000 seconds. And maybe I can take a step of 20 this time. And let's just recalculate everything. See what we get. So it takes slightly more time to calculate because we have 50 time increments this time. Let's have a look at what we have in the results. So let's look at the temperature. Let's go to the last time step and let's rescale everything. And now I think we are much, much closer to what I was expecting, which is 136.7 degrees Celsius, which is very good. Let's have a look at the curve. And let's plot only the temperature. And now I think we are pretty good. You see the temperature go from 0 to 1000, and it starts more and more to converge towards 140 degrees. So I am now getting a transient simulation, which is getting close to my steady state simulation results. So everything is cool. Now you might think that yeah, okay, you took a source transient function which goes from 0 to 10 seconds and basically increases. That's so short in comparison to this simulation time. And you would be right. It's basically useless. I should probably do that from 0 to increase it to 0 to 400, see what happens. And but that's just a tutorial, right? That's to show you how it works. And I hope that I achieved what I wanted to do, which is to show you how to do this steady state and transient simulation with Salome and Codaster. But thank you so much for watching this video, and if you like it, please give it a thumb up. Please subscribe to my YouTube channel. Please share with your engineer friends. Thank you so much again, and thank you for following the blog. See you in the next videos.